Okay, so today I will talk about our recent work on domain wall qubits on magnetic racetrack. So this work is done with Stefano Ianiana and also Daniel at Basel, and also our experimental friends Banabir and also Stuart from Max Planck Institute. Okay, so here is the outline of my talk. So first, I will very briefly mention the background, and then I will move on and define what is a domain wall qubit, and then I will discuss how to shuttle this domain wall qubit on the racetrack. And of course, we need to discuss how to implement single qubit rotations and also two qubit gates. And finally, I will discuss how to read out the qubit and also its lifetime. Okay, so let's start with this background. So today's main role is this domain wall. And let's imagine we have a magnetic nanowire as we sketched here. And on the one end, we assume all the spins are pointing upwards. And on the other end, we have all the spin pointing downwards. Then the spins within this region, they would smoothly connect these two domains, right? And this kind of spin textures, like what one we sketched here, is what we call a magnetic domain wall. And there's one typical length scale associated with the domain wall is what we call the domain wall width, and we denote as lambda here. And one important application of this magnetic domain wall is the well-known racetrack memory, where we use this domain wall as a classical bit to store the this classical information. And it is proposed by Stuart Parkin a while ago. And after that, there are not experimental efforts along this line. And now people can actually manipulate and control the domain wall motion very easily through different means. For example, by applied magnetic field, or like apply an electrical current or spin current. One very impressive thing is that now we can drive this kind of a magnetic domain wall within the magnetic nanowire, or we call it a magnetic racetrack, with a super fast speed, even over like 1,000 meter per second. So the question we try to ask in our work is, can we go beyond this picture, right? So one natural thing we can think about is how about push all this kind of setup into the quantum regime and ask, can we use this kind of domain wall as a quantum bit instead of just a classical bit? For example, for quantum computing or quantum communication. So that's the question we try to ask. Okay, so to use this magnetic domain wall as a quantum bit or qubit, the first question we should ask ourselves is which degree of freedom we want to use to store this quantum information, right? And before we dig into the details, I would like to give you a very rough idea. So here we propose to use the chirality of the domain wall to store this quantum information. And so what is the chirality of the domain wall? So like, for example, as we sketched here, so on the one end, we have one domain with spin pointing downwards, and on the other side, we have the domain with spin pointing upwards. So there are different ways to smoothly connecting these two domains, right? For example, one way is to rotate the spin from down to up counterclockwise as we sketched here, this upper case. And if we move all the spins onto this spin space or the order parameter space, this would correspond to this radial trajectory, as we can see. So first, the spin is pointing down, and then we rotate the spin counterclockwise, and we would eventually arrive at the spin up state. Okay, so in this spin space, as you can see, this red trajectory is basically as the azimuth angle phi is 0, so phi equals 0. And another way to connect to smoothly connect these two domains is to rotate also from down to up, but now clockwise, as we sketched in this lower case. And of course, we can also move all the spins onto this spin space, right? Now, this would give us this blue trajectory. First, we also have the spin point downwards, and then if we rotate the spin clockwise, we would follow this blue trajectory, and eventually we will also arrive at this spin up state. And this blue trajectory would correspond to this azimuthal angle phi equal to pi, right? And so the idea of us is, to use this kind of a different chirality. So we as a pseudo spin degree of freedom. So namely, for example, we can use this positive chirality state as a spin up state and this negative chirality state as a spin down state. Okay, so here just to refresh your memory, it's just a DiVincenzo criteria, and it's a screenshot from the Wikipedia page. So the first 5 points they are for quantum computing. So namely, we should have well-defined qubit, and also we should be able to initialize this qubit into a well-defined state, and we should also be able to read out this qubit. And of course, we should be able to implement single qubit rotations and also 2 qubit gate. And of course, this qubit must be non-lived. And these last 2 points, they are for quantum communication. Namely, we should be able to convert a stationary qubit into a flying qubit, and also from a flying qubit to a stationary qubit. Besides, we also require that we can move this or when this flying qubit moves from one location to another, the process should be coherently enough such that there would be no information loss during this traveling process. So hopefully I will convince you that the proposal of ours, this domain wall qubit, can be utilized for both quantum computing and also for quantum communication. Okay, so let's start with some model. We consider a very simple two subnet is called a one-dimensional ferromagnet. And so as we sketched here, so each spin here should be understood as a large spin together with a smaller spin in the opposite direction. So this kind of system can be described by antiferromagnetic order together with a ferromagnetic order. And we would assume, we can describe this antiferromagnetic order with a neo vector n. And also we assume the net spin within the unit cell is SE. It's basic this SE basically is the difference of this spin length within the unit cell, right? And of course, we can write down this low energy description for this one-dimensional system. The kinetic energy is given by 2 terms. So the first term is for the antiferromagnet, and the second term is for the ferromagnet. So the physical meaning of every term should be clear. So for example, by the way, this H is the applied magnetic field. So for example, we can expand this square, right? We would get 3 terms. So the first term would be quadratic in the time derivative, which is the standard kinetic energy for the antiferromagnet. And we also have a cross term, which is linear in the applied magnetic field H, and also linear in this time derivative, meaning that it is a geometric phase. So the physical meaning of this cross term is very clear because imagine we have an antiferromagnet and we apply a magnetic field. Then this magnetic field would create a net magnetization proportional to this magnetic field. So this net magnetization would accumulate a spin-Berry phase in the dynamics, and that is governed by this cross term. And the last term, which is basically h cross n squared, this is the easy plane anisotropy due to the applied magnetic field. So namely, when we apply a magnetic field, this near order would like to be perpendicular to this applied magnetic field. And again, we have the part for the ferromagnet. This is just the standard barrel phase term, right? And this capital A is this spin collection defined in the standard way and with the prefecture proportional to the net spin density, SE. Okay, so of course, so we can also write down this potential energy. There are also two terms. Two parts. So in the first part, we have two terms. So the first term just tells us that the spin texture must be smooth. And the second term, which is what we called easy z-axis anisotropy, and we denote as capital Z, Z kz. And this term just tells us that a spin would like to point along the z direction. It can point along the positive z direction or negative z direction, and just to minimize this term. And similarly, we have another easy xz plane anisotropy. Due to this term, the spin would like to point, want to stay in the xz plane to minimize this term. And the last term is the standard Zeeman coupling due to the applied magnetic field, and also is proportional to this spin density. Okay, so here are some remarks. So first, we have rescaled this spatial parameter x from x to lambda x. So now this x in our expression is dimensionless, and we basically measure the distance in unit of domain or width. Here, lambda is the domain or width, which is given by this square root of j, the exchange divided by this easy axis anisotropy. And also, one important thing that is this kind of a high energy hierarchy in our problem. So we assume the highest energy scale is the largest energy scale is this exchange coupling, which is about room temperature 300 Kelvin. And then the second largest energy scale is this easy axis anisotropy kz, which is about 3 Kelvin. And if we plug those numbers into the expression, we would get a domain wall width about 5 nanometers, which is experimentally feasible in the lab. And other energy scales like this Zeeman coupling and also this easy plane anisotropy, they're much more smaller compared with other energy scales. So therefore, we can actually treat this second part as a perturbation of the first term, right? And okay, so let us assume this boundary condition that all the spin on the right side, on the left side, they all point down, and on the right side, they all point up. In this case, if we minimize this first term, the first part, we would get the standard domain wall configuration as we wrote down here. There are actually two important parameters in this expression. So one is the capital X, which physically stands for the position of the domain wall. This is a zero mode because of this translational symmetry of your potential energy in real space, right? And meaning that we can place this domain wall anywhere within the nanowire. They cost the same energy. And another important parameter is this azimuth angle phi, which is basically the azimuth angle of your spin texture in the spin space. Remember, we just mentioned before that when this azimuth angle phi equals 0, this is basically this red trajectory. This would correspond to this a positive chiral state. And similarly, when phi equals pi, which stands for this blue trajectory, this would give us the negative chiral state. In principle, this azimuth angle phi can be any value from 0 to 2 pi. And also, if we only care about the first term, then all these values from 0 to 2 pi, they are equally preferred because of the U1 symmetry around the z-axis in the spin space, right? And of course, if we take the first term here into account, then this term, it would break this U1 symmetry into the Z2, And in this case, this phi equal to 0 and phi equal to pi states, they are preferred. And they are basically the two chirality states we care about. Okay, so so let's move on. And with that in mind, we can write down the action for these two low energy modes, capital X and phi. And we have three pieces. The first line just action for this azimuth angle phi, and the second line is the action for this spatial degrees freedom X. And also, the last line is the coupling between these two variables. And now let's look at the first term here. It's basically the standard kinetic energy for the azimuth angle phi. And the first term here is the we just mentioned before, is the easy plan anisotropy that would due to this term, this phi equal to 0 and phi equal to pi states they would be preferred. And the second term here is basically the easy plan anisotropy due to the applied magnetic field. And turns out with the energy scales we assumed before, this term would be much smaller compared with the first and the last terms. So we would neglect this term in our discussion later. And the last term again is basically the Zeeman coupling. Okay, so for this second line is the action or the Lagrangian for this spatial degrees freedom X. And here we add like confining potential for domain wall with a frequency omega p. And the last term is basically the coupling between this X and phi due to this spin Barrel phase effect. Therefore, we have two terms here. So one term is due to the net mechanization due to the applied magnetic field, right? This net mechanization would accumulate spin Barrel phase. And another contribution is also the net mechanization within the unit cell, which, as you can see, is proportional to SE. So this net mechanization would also accumulate spin Barrel phase. Okay, so that's all this action for this, all the low energy modes that we care about. And one important observation is that this action is proportional to the domain wall size. It just tells us that if the the system size is the domain wall is larger, the system is more classical. At this point, we can already guess that if this kind of the lifetime of this domain wall qubit, basically the quantum coherence would decay within a lifetime that this lifetime would be inversely proportional to this domain wall size. And we will show this explicitly later. So here here we will first define this domain wall qubit using this first part, and later on we will implement this two qubit gates and also single qubit rotations using this spatial degrees freedom X and this coupling. Okay, so now let's look at the potential energy of this azimuth angle phi. And here we have introduced the two dimensionless magnetic field just for convenience, this Bx and By. So first, let's turn off this Bx. So we basically have only this magnetic field in the y direction as we sketched here. In this case, the energy profile is this kind of a double well potential form. And so this phi equal to 0, as I said before, is basically the positive chirality state, and the phi equal to pi is the negative chirality state. Of course, when phi equal to minus pi, it is also a negative chirality state, right? And this positive chirality state can tunnel to this negative chirality state. For example, through this through this barrier, this process A, and so basically through this barrier at phi equal to minus phi at phi equal to pi over 2. Okay, wait a second. Okay, so this phi equal to pi over 2 is basically this positive y-axis, saying that in this case, this tunneling process is basically, this spin texture along this blow trajectory, they go out of plane, and then through this positive y-axis, they tunnel to this blow trajectory, right? And another tunneling process is through this tunneling barrier. Sorry, this barrier at the phi equal to minus pi over 2. That is basically the minus y-axis. So saying that this textures would go out of plane and then through the minus y-axis, and we can tunnel to this this phi equal to minus phi equal to pi state, which is basically the negative chiral state. And we should notice that the effect of this by, this by is just to suppress this energy barrier at this phi equal to pi over 2, and increase the energy barrier at phi equal to minus pi over 2, such that the tunneling rate of this process A is exponentially larger compared to this tunneling this process B. And physically, it is also it also makes sense because when you apply a magnetic field in the y direction, then of course all the spin textures would prefer to tunnel through the positive y-axis, right? And for this reason, we would only focus on one tunneling one double well potential and neglect this process B. Okay, so now let's discuss the effect of this magnetic field Bx along this racetrack. The meaning of this, the effect of this Bx is also very clear because as you can see that when we apply a magnetic field along this racetrack in the x direction, then it is clear that this positive chirality state would be preferred compared to this negative chirality state. Therefore, this Bx would, generally speaking, would give us a detuning between this positive chirality state and negative chirality state. In terms of this potential energy, as we can say, because of this finite Bx, we would have a lower energy for this positive chirality state, right? And now let us project the dynamics of this azimuthal angle phi onto these two noise energy states, two chirality states. Then we would get two terms. The first term is the detuning proportional to sigma z with a prefactor epsilon. This epsilon is basically controlled by this applied magnetic field along this racetrack Bx. And similarly, we have a tunneling process that would give us a sigma x. And with the tunneling rate Tj, which is controlled by this energy barrier. And very importantly, we should point out that both parameters, they are tunable through external magnetic fields, Bx and By. And this tunability is very important for us if we want to use this domain wall as a quantum bit. Okay. So once we have this Hamiltonian, of course, we can write down the energy splitting of this qubit. It is given by the square root of the tunneling Tj square plus this detuning epsilon square. So here we plot this tunneling splitting as a function of the detuning. And as you can see, when we apply a magnetic field in the positive x direction, we would get a negative detuning. And in this case, this positive chirality state is preferred. And we can use this as an approach to initialize our state into states with certain chirality. And with the parameters we assumed, one can show that this Tj, this tunneling rate, is about 20 gigahertz. And when we So here we only consider the dynamics of this azimuth angle phi. So it turns out in the presence of this dynamics of the spatial degrees freedom, this TJ would be suppressed by an order of magnitude, as we will see in the next slide. Okay, now let us consider the total dynamics, the whole dynamics. So we have this azimuth angle phi, and we also have this spatial degrees freedom and this their coupling. And so in this case, for simplicity, we assume this Bx equals 0. So there is no applied magnetic field in this x direction along the racetrack. So we can project the dynamics of this azimuth angle phi onto the qubit subspace. In this case, we only get this tunneling process, this sigma x, with the tunneling rate Tj. And for the first two terms, first let's forget about this sigma z term. Then it's just a p squared plus omega square x square, which is the standard harmonic oscillator describing this the spatial degrees freedom x. And x naught here as a function of the time is is a classical variable that describes the location of this domain wall that can be controlled externally. And this coupling between phi and x, when we project onto this qubit subspace, we would get this beta z sigma z. Effectively, this is just a spin orbital coupling between this spin space and this real space, real space dynamics, right? And again, this kind of effective spin orbital coupling is due to the spin Barré phase effect. That's why in the expression of this beta z, there are two terms, there are two contributions. One is due to the net spin in the unit cell, which would accumulate spin Barré phase. And another term is the net spin, generated by this applied magnetic field, which would also accumulate the Barré phase. And here we introduce two important length scales. First one is the so-called spin orbital length, and it turns out it's about 0.1 nanometer. So the meaning of this spin orbital length is that this is basically the distance the qubit need to travel to flip the spin. And and we also have this harmonic length, which is controlled by this omega p, which is basically the confining potential for this domain wall, which is around 2.25 nanometers. And to study this kind of shuttling effect, it's better to move into a frame that moving together with this domain wall. So to do that, we perform unitary transformation. It's basically a displacement operator, and this would give us like a velocity term, a term that is proportional to the velocity. Okay, still we have this spin orbital coupling. To see the effect of this coupling, we perform a gauge transformation, which is basically a spin-dependent displacement within this momentum space, right? And then we project the whole dynamics of this spatial degrees freedom onto its ground state. So eventually we arrive at this effective Hamiltonian. And we notice that now we get effective detuning. At the very beginning, we have no detuning, right? So this detuning parameter, this epsilon tilt, is proportional to the velocity v. And in this case, the reason why there is such a detuning term is also clear, because when we move this domain wall in certain direction, we explicitly break this inversion symmetry in the spin space, in the real space, and we know the real space is linked to this spin space through this spin Barré phase effect, and therefore effectively we will break this inversion symmetry in the spin space. And that's why we have this detuning. And again, like what I mentioned before, this tunneling rate would also get renormalized, and in this case, is suppressed. And now the approximately is about 3 gigahertz. And of course, we cannot just shuttle this domain wall with infinite large speed, because when the speed is too large, we would have a higher probability to excite higher energy states. That's not what we want, because we want to stay within this ground state or this qubit subspace, right? So that would give us a constraint. Is in this case, we would the maximum velocity we can shuttle is about 100 meter per second. Okay, so with this Hamiltonian, we can write down this physical qubit splitting, and which is basically given by the square root of this epsilon square plus the tunneling Tj square. And by the way, here we have restored this Bx. This is just shift this detuning a little bit. And in this case, here we plot this physical splitting as a function of Bx and By. And as you can see that one feature is that when we increase this By, the tunneling splitting, the qubit splitting would first increase and then decrease. The reason why it's like this is first clear, because when we increase the By at the very beginning, remember that the effect of the By is to suppress the tunneling barrier. Then we would have a larger tunneling rate. However, when the By is very large, then we would get a very relatively large net magnetization due to this applied magnetic field, and then we would get another spin barrier phase effect, or effectively this spin orbital coupling that would suppress this tunneling process. Okay. So now let's talk about a single qubit rotations. To realize this kind of a single qubit gates, there are several ways. So one way is to just to shuttle this domain wall with a constant speed. So because of this Hamiltonian, it's in this form, and then when we shuttle it with a constant speed, we would naturally get a spin rotation around the m-axis. This m-axis is staying within this xz plane. And this the direction of this rotation axis m is also tunable, because the theta angle is controlled by this ratio of this tunneling rate Tj and to this detuning epsilon. So by tuning this By and also the shuttling speed or the Bx, we can change this angle theta. Okay, so we can also implement this single qubit gate by shaking this qubit or this domain wall within the racetrack. So to see that, let's assume this velocity has this following this profile with the amplitude V0, and also this st is the envelope function. For simplicity, we can assume it to be 1, and also the driving frequency is omega d, and also the initial phase is phi naught. So as the resonance and also we assume in the rotating frame, in this case, one can easily show that the Hamiltonian would be a sum of sigma x and sigma y. So in this case, when the as we can see easily, when phi naught, the initial phase is 0, we would get a single qubit rotation around the x-axis. And similarly, when the phi naught is pi over 2, then we would get single qubit rotation around the y-axis. And in this case, the gate operational time is also very clear. It's basically given by the spin orbital length, which is remember the distance that one needs to travel to flip the spin, divided by the velocity. And in our case, it's approximately 0.1 nanosecond. Okay, so to implement the 2-qubit gates, we need to consider, 2 parallel racetracks. And in this case, generally speaking, the interaction between these 2 racetracks would be in this form. Here, alpha and beta, they are spin indices. And imagine we have a magnetic magnetic domain wall, in this upper racetrack with azimuthal angle phi1 and versus the position x1. And now let us assume that the azimuthal angle of the domain wall in the second racetrack is phi2, and their distance is denoted as this capital D, which is a function of time in general. And in this case, similarly, we project the whole dynamics onto this qubit subspace. In this case, we would get an effective interaction between these 2 qubits, which is sigma 1x tensor product sigma 2x. And one can say that these 2 qubits would, the interaction would decay exponentially when their separation D is larger than the domain wall width. It just tells us that those 2 qubits, they will not talk to each other if they couldn't see each other. Okay, so to implement this 2-qubit gate, we just need to shuttle 1 qubit, for example, the upper one from left to right. So in this process, let's assume the velocity is a constant. Then, we realize, in this process, it's basically a unitary transformation, and in this form. And as we notice that when the prefactor is pi over 4, it's basically a CNOT gate. And just to give you an idea, so when this interaction between these 2 domain walls is about 50 megahertz, which is feasible according to our experimental friends. And then we just need to shuttle this domain wall with a velocity 20 meter per second. And in this case, the gate operational time is given by the time for the 1 qubit to go across the second qubit. It's basically given by this domain wall width divided by the velocity. It's about 0.2 nanosecond. Okay, so finally, let's talk about, okay, not finally, but let's talk about qubit lifetime. So, there are a lot of quartz particles around. For example, we have photons, electrons, if the system is conducting. Then due to this kind of environmental degrees freedom, this azimuthal angle phi and x, they would fluctuate, right? Due to this fluctuation, we would get a decoherence of this qubit. To work it out, the idea is first we work out the friction force acting on those 2 variables, which is basically the prefactor, this dissipative factor alpha tilde is proportional to the so-called Gilbert damping, which is a phenomenological parameter, and also the size of the system, right? And as you can see, once we have this kind of dissipative force, according to the fluctuation dissipation theorem, we can write down this fluctuation in the potential energy directly. So this random variable C has a 0 mean, and also the spectral function is given by this form with the prefactor, alpha tilde. And as you can see, because of the fluctuation in the position x, and it would give us, some, random fluctuation in this, also in this velocity, and eventually it would give us a fluctuation in the detuning. And also, without fluctuation, we have a perfect double well potential, but because of this term, we would have some fluctuations at each point. And of course, this kind of fluctuation would also give us, a detuning fluctuation in the detuning, and also because the tunneling barrier is also fluctuating, so we would get a fluctuation proportional to sigma x. So once we have this fluctuation qubit Hamiltonian, we could write down this relaxation rate and also the dephasing rate directly. So one important thing we should notice is that this pure dephasing rate, this gamma phi, is proportional to this cosine theta square, which is again proportional to this detuning. Meaning that when the detuning is zero, namely when my magnetic field along this racetrack is balanced with this shuttling speed, then this detuning is zero and this pure dephasing is zero. And this is basically what we call a sweet spot. And here we show this pure dephasing, it's a dephasing rate. As you can see, so here we assume this velocity is zero. Then when Bx equal to zero, this dephasing process is minimal. And of course, in this case, when Bx equal to zero, this relaxation rate would be maximum because it's proportional to the sine theta square. Of course, we know that general speed, usually this T2 would be the limiting factor. So we would like to, extend the T2. And finally here in this first plot, we show this lifetime as a function of the velocity in different temperatures. And just to give you an idea, so when we shuttle the qubit at a velocity 20 meters per second, and also the temperature 50 millikelvin, we get a temperature, we get a T1 about 0.2 microsecond, and the T2 about 0.15 microsecond. So the coherent shuttling distance is about 3 micrometers. So this coherent shuttling distance is basically the distance that this qubit can travel within its lifetime. And the quality factor we have is around 1000. Okay. So finally, for the qubit readout, we can first, of course, we can use NV center to to see like this the texture of this domain walls, and another way to read out is to use spin qubit. For example, when the system is conducting, we can put a paramagnetic dot nearby. Then this dot can this electrons can tunnel to this dot, and this dot would be polarized, and the polarization of this dot can be measured easily. And otherwise, we can also now couple a spin qubit magnetically to this domain wall qubit, and in this case, in this case, by reading out this spin qubit, we can also get the information of this chirality of this spin of this domain wall qubit. Okay, finally, I hope I have convinced you that our proposal, this domain wall qubit, can be used not only for for this kind of quantum computation, like other qubits, like spin qubit or superconducting qubit, but we can also use it for quantum communication, because in this case, as I showed, we can naturally move this domain wall qubit on this magnetic racetrack, and also we can coherently move this domain wall over a distance like a micrometer distance. So it's pretty large distance. And yes, that's okay. That's basically what I want to tell you. And thank you for your attention. And here are my collaborators, Stefano, Banabir, Stuart, and Elena, and Daniel. Okay, thank you.